In this video we are going to look at 3 further examples of proof by induction. In the previous video we learnt that to produce a proof by induction for a result about the positive integers, then we must first of all show that the result is true for n equals 1, and then secondly we must show that if the result is true for n equals k, then it must also be true for n equals k plus 1. Okay, so let's look at our first example. We're told that we've got the matrix 3, 2, 0, 1, and we have to prove by induction that if n is a positive integer, then m to the power n, that's the result of multiplying m by itself, n times, is 3 to the n, 3 to the n take 1, 0, 1. So, following our normal proof by induction method, we start off by saying, right, we must show that the result is true for n equals 1. When n equals 1, the left-hand side is m to the power 1, and m to the power 1 is just m, which is the matrix 3, 2, 0, 1. The right-hand side of the result, when n equals 1, is the matrix 3 to the power 1, 3 to the power 1 take away 1, 0, 1. Remembering that 3 to the power 1 is just 3, that straight away gives me 3, 2, 0, 1 as required. So we've got the left-hand side of the result does equal the right-hand side of the result when n equals 1, so the result is certainly true for n equals 1. Our second stage, we assume that the result is true for n equals k, and we must then deduce that the result is also true for n equals k plus 1. So, what we've got to try and do is we've got to consider m to the k plus 1, and we've got to try and show that it's equal to the result when little n is equal to k plus 1. In other words, we've got to show that m to the k plus 1 is the matrix 3 to the k plus 1 as the top left entry, 3 to the k plus 1 take away 1 as the top right entry, 0 as the bottom left entry, 1 as the bottom right entry. Well, m to the k plus 1 is the same thing as m times m to the k. Now we are in this step assuming that we already know the result is true for n equals k. In other words, we are assuming that m to the k is the matrix 3 to the k, 3 to the k take 1, 0, 1. So we can write m to the k plus 1 as being m, that's 3, 2, 0, 1, times by 3 to the k, 3 to the k take 1, times 0, 1. So, performing the matrix multiplication, the top left entry is going to be 3 times 3 to the k plus 2 times 0. And that simplifies just to 3 times 3 to the k. The bottom left entry is going to be 0 times 3 to the k plus 1 times 0, which just gives us 0. The top right hand entry is going to be 3 times 3 to the k take away 1, add 2 times 1. Multiplying that out, I've got 3 times 3 to the k, take away 3, add 2. In other words, I've got 3 times 3 to the k, take away 1. And the bottom right hand entry is going to be 0 times 3 to the k minus 1, add 1 times 1, which simplifies just to 1. And all we have to do to move from our expression for m to the k plus 1 to our target expression is just remember that 3 times 3 to the k is the same thing as 3 to the 1 times 3 to the k, which is the same thing as 3 to the k plus 1. So 3 times 3 to the k is the same thing as 3 to the k plus 1, and 3 times 3 to the k take away 1 is the same thing as 3 to the k plus 1 take away 1. So we've actually achieved our target expression. So we now know that if the result is true for n equals k, then it is also true for n equals k plus 1. We know by the first step that the result is true for n equals 1, so that certainly means now I know the result is also true for n equals 2, using the second step. Using the second step again, that now means I know that the result is true for n equals 3. Using the second step again, I now know it's true for n equals 4, and so on, all the way along the positive integers. So we now know that the result is true for all positive integers, n. Now our second example considers the sequence of numbers defined by xn is 7 times 3 to the power n, take away 6n, take away 3. And we've got to prove by induction that for all possible values of n, that's all positive integers n, the number xn is going to be divisible by 12. So again, we will start with the first step, which is to prove the result in the case when n equals 1. Now the value of x1 is fairly easy to work out. It's 7 times 3 to the power 1, take away 6 times 1, take away 3. So that's 7 times 3, which is 21, take away 6, take away 3, which gives me 12. And 12 is certainly divisible by 12. So x1 is divisible by 12, and we've got the result is true for n equals 1. x1 is certainly divisible by 12. For the second step, we're going to assume that the result is true for n equals k, and deduce that the result must also be true for n equals k plus 1. Okay, so we've got to consider what we can do with xk plus 1. Now we know that xk plus 1 is defined to be 7 times 3 to the k plus 1, take away 6 lots of k plus 1, take away 3. In other words, we can say that that is 7 times 3 times 3 to the k, because we know 3 to the k plus 1 means 3 to the 1 times 3 to the k. Take away 6k, take away 6, that's multiplying out the brackets on 6k plus 1, and we've got take away 3. Or tidy that up, we've got 3 lots of 7 times 3 to the k, take away 6k minus 9. Now we need to just be a little bit careful here. We know that xk is 7 times 3 to the k, take away 6k, take away 3. So a little bit of rearrangement of that tells me that 7 times 3 to the k is xk plus 6k plus 3. So if we substitute that in to the expression we've got for xk plus 1, we've got xk plus 1 is 3 lots of xk plus 6k plus 3. Take away 6k, take away 9. In other words, xk plus 1 is 3 lots of xk plus 18k plus 9, take away 6k, take away 9. And that simplifies to 3 lots of xk plus 12 times k, Now, we're assuming that the result is true for n equals k. And if the result is true for n equals k, then that means that xk is a multiple of 12. So 3 times xk must be a multiple of 12. Certainly we know that 12k is a multiple of 12. So we've got 3xk is a multiple of 12, 12k is a multiple of 12. So 3xk plus 12k is one multiple of 12 added to another multiple of 12, which must give us a multiple of 12. So we know that xk plus 1 must be a multiple of 12. So, if the result is true for n equals k, then it must also be true for n equals k plus 1. We know the result is true for n equals 1 by step 1, so the second step tells me it must also be true for n equals 2. We know the result is true for n equals 2, so the second step now tells me it must also be true for n equals 3. And we can carry on along through all of the positive integers and deduce that the result is therefore true for all positive integers n. Now for our final example, we're going to consider the inequality 240n squared is less than 5 to the power n. And we want to find out for which positive integers is this inequality valid. Well, if we do some trial and error on a calculator or work a little bit more systematically and produce a spreadsheet, we might produce a table of results looking something like this. And we can see from this table of results that the inequality 240n squared is less than 5 to the n is true for n equals 6, 7, 8, 9, 10, 11, 12. So we might come to the conclusion, or to the guess, or the conjecture would be better than the conclusion at this stage. So we might come to the conjecture that the inequality 240n squared is less than 5 to the power n is true provided n is greater than or equal to 6. And what we're going to do now is we're going to produce a proof by induction that this result is indeed correct. So, we're going to prove by induction that if n is a positive integer with n is greater than or equal to 6, then 240n squared is smaller than 5 to the power n. So as always, we're going to first of all start off with the first step. Now the first step in this case is not going to be with n equals 1, because the result isn't true when n equals 1. The first value for which the result is true, we saw from the spreadsheet, was n equals 6. So we're going to clamber onto the ladder not at n equals 1, but at n equals 6. So when n equals 6, the left-hand side is 240 times 6 squared is 8,640, whereas the right-hand side is 5 to the power 6, which is 15,625. So 8,640 is certainly less than 15,625. So the result 240n squared is less than 5 to the n is certainly true in the case when n equals 6. And then our second step, assuming the result is true for n equals k, where k is a number which is at least 6, deduce the result is also true for n equals k plus 1. Okay, so what we've got to do is we've got to try and show that 240 times by k plus 1 squared is definitely going to be less than 5 to the k plus 1. Now 240 times k plus 1 squared is the same thing as 240 times by k squared plus 2k plus 1. Now, we know that k is greater than or equal to 6. So we can certainly be certain in our own mind that 2k plus 1 is definitely going to be less than 2k plus k, because k is more than 6, so it's definitely more than 1. So we've got 2k plus 1 is definitely less than 3k. What's more, 3 is definitely less than or equal to k, because we know that k is greater than or equal to 6. So we can certainly say that 3 times k is definitely less than k times k. So I've got 2k plus 1 is less than 3k, which is definitely less than k times k, which is k squared. So we know that 240k plus 1 squared is the same thing as 240 times k squared plus 2k plus 1. And we know that 2k plus 1 is definitely less than k squared. So we can therefore say that 240k plus 1 squared is definitely less than 240 times by k squared plus k squared. So we've got 240 times k plus 1 squared is definitely less than 2 lots of 240k squared. We're assuming the result we're working towards is true for n equals k. So 240k squared is less than 5 to the power k, which enables me to write that 240 times by k plus 1 squared is less than 2 lots of 5 to the k. But 2 lots of 5 to the k is definitely less than 5 lots of 5 to the k, which is 5 to the k plus 1. In other words, we've got 240 times by k plus 1 squared is definitely less than 5 to the k plus 1. So we've obtained our target result. So we know that if the result is true for n equals k, then it is also true for n equals k plus 1. By the first step, we know the result is true for n equals 6. So using the second step, we now know the result is true for n equals 7. Using the second step again, we now know the result is true for n equals 8. And we can go on all the way up to the integers and deduce that the inequality 240n squared is smaller than 5 to the n will be true for all positive integers which satisfies n is greater than or equal to 6. So we've looked now at 3 further examples of proof by induction, and here are 3 examples that you might like to try. Certainly have a go at 1 or 2 of them, even if you don't have a go at all 3 of them.